Okay, welcome back to lesson 3.1. We're going to start talking about the applications of velocity and acceleration in this part of the video. So a couple of definitions that we need to know about are the words position, velocity, and acceleration. So position is just your location at some time t. In symbols, we say s at t for position. Now, when I get a position that's positive or negative, it does have a meaning for me. So I do need to think about that. Positive or negative is going to indicate direction for me. Most of the time when we use a position function, positive means right and negative means left. But sometimes it'll be like positive is up and negative is down. Now, when we talk about velocity, velocity is what we think about as speed in real life, but speed does not have a direction. Velocity does. Velocity is the rate of change. It's how quickly is the position changing. So it's the rate of change of position. And again, the velocity changes based on the time. So we always talk about the velocity at time t. In symbols, velocity function is v at t, but that's the same because it's the rate of change of the position. It's the rate of change of s at t, or the derivative of s at t. And this is one of the reasons that we're interested in taking the derivative, because it tells me the velocity. Acceleration is the rate of change of the velocity. And again, at time t. So it tells me how quickly is my speed changing. And so my acceleration is going to be equal to the rate of change of the velocity. So it's going to be v prime. But remember that v is s prime, so I'm taking the derivative of the derivative. And so the acceleration is actually the second derivative of the position function. And this is one of the applications, and this you can imagine in engineering is something that we're interested in. Like for instance, if you were to talk about like a gear wheel, you might be interested in the position of a certain part of the gear wheel. You might be interested in the speed that it's changing. You might be interested again in the acceleration as well of that piece of machinery or other pieces of machinery within. In our example, though, we're looking a little bit simpler because we're just exploring the idea in high school. We're going to be looking at a soccer ball. So the height of the soccer ball, we're looking at a height function, so we're talking about positive is up and negative is down. We've got time t after it's kicked into the air. It's going to be given to us by this function here. It's kind of reminding us of like grade 10 math, right? The parabolas. H is in meters and t is in seconds. For this function to be true, time has to be greater than or equal to 0. So the first thing we want to do is determine an equation that will tell me the instantaneous rate of the change of the height. So if I want the rate of change of the height, that's asking me for the velocity, is one way for me to interpret that. And so I'm going to take, I want the rate of change of the height, I want the derivative of the height. So I'm going to take that exponent 2, bring it down and multiply it by the negative 4.9, subtract 1 from the exponent, and then taking the derivative of the second piece here, that's just 3.5, and the derivative of 1 is just 0, so you can write a plus here if you want. Now it asks me to find this equation. I'm going to interpret this. This is also the vertical velocity of the ball. So if I were to plug in a certain t value to this and I got a positive answer, then it would tell me that the ball was moving upwards. And if I got a negative answer, it would tell me the ball was moving downwards. All right, in part B of this question, we're determining the vertical velocity of the ball half a second after it's kicked. And then I want to figure out at what other time will the ball have the same magnitude of vertical velocity. So when we talk about the magnitude, remember another word for magnitude is like the absolute value. So it's going to have the same sign, or sorry, the same value, but it could be a different direction. So same speed, but could be a different direction. Okay, so this question asked me for the vertical velocity first at half a second. Now I already know that the vertical velocity, I'm just going to copy it from the other question, is negative 9.8 t plus 3.5. And so we're going to find the vertical velocity at half a second. So we'll sub in that number. I don't need to write at t equals 0.5 because I've got function notation. So it's right there. And when I type that into my calculator, I get negative 1.4. Now the units for this one, because I want to be thinking about what does this mean, the units for the velocity are going to be, because it's a derivative or a rate of change, it's going to be the rise unit over the run unit. So here our rise unit is the height unit, meters, and our run unit is seconds, the time unit. I'm going to interpret this question, or this answer, sorry. It tells me that the ball is falling because I got a negative answer, right? Or decreasing. The ball is falling at a rate. So the height is decreasing is another way for me to say that. Now, the ball isn't always falling at that speed, so you actually have to specify when is that happening. It's happening at 0.5 seconds. All right, now the second part of the question says, at what other time will the ball have the same magnitude of vertical velocity? So what the second part of the question is asking me for is, when is the value of the derivative equal to positive or negative 1.4? I want to find what are the times. So for what values of t? And remember, I already know when it's going to equal negative 1.4. But what I would do here to solve this is I would plug in the derivative equation. So I've got negative 9.8 t plus 3.5. I want to know, when does that equal 1.4, or when does it equal negative 1.4? Now, because it's a linear expression, you actually already have the answer for this one here when it equals negative 1.4, but you could double check your work. You should get 0.5 when you rearrange this. And that is what happens here. Now this one here, I'm going to have to rearrange to solve. So I'm going to bring the 3.5 over and subtract it. And then I'm going to divide out the negative 9.8. So at about 0.21 seconds, I'm going to have the same speed, but it's actually going in the opposite direction because it's the positive velocity. If I want to take a look at this on the graph, so here's the graph of that parabola. I've got the times across the bottom here. We were looking originally, they gave us the speed at half a second, or well, we calculated the speed at half a second. And you can see here that when I draw the tangent line, remember the speed is related to this tangent line. The speed is the slope of this tangent. And so the slope of this line was negative 1.4. That makes sense, it's negative, it's heading down. What we found is that there's another tangent line over here that has the same steepness, it's just heading in the opposite direction. So the slope over here was positive 1.4. And if I head down here, it's actually happening like right around 0.2 seconds. And it's just a little bit past it. And then we'll write a sentence about this one as well. So just the opposite of before. Before it was falling, now it's rising. Right, part C says, at what point will the ball reach its maximum height? So again, we're using our calculus techniques here. Sometimes it can be tempting. Since you already have these two x values, you know that the vertex is going to be in the middle. But it's not always going to be a parabola in all of our questions. So we want to have a calculus technique for this. What is going to happen though is whenever I'm at a maximum, and we're going to be looking at this throughout the chapter, is that when I'm at a maximum on a curve, and maybe it's like got a whole bunch of, maybe it's like a quintic function and it just keeps going. But whenever I reach that maximum there, imagine drawing the tangent line in. It's going to be a horizontal line. So when I'm at the maximum, the derivative value or the slope of the tangent will be equal to 0. So if I want to find at what point, it's asking me to find the t values. And I want to find the t that makes this statement true. So we're going to plug in our derivative here. Whoops. We know the equation of the derivative. And we want to know when does it equal 0. And I would include this actually in my equation, or in my solution. And then I can rearrange and solve this guy. So bringing over the 3.5 and then dividing out the negative 9.8. And I get about 3.6 seconds. It does ask me as well in this question, what is the maximum height? So if I know that the maximum height happens at 0.36 seconds, all I have to do to find the height at 3.6 seconds is plug it into the original function. So I'm not using the derivative here. I actually want to find the height. So plugging it in to the negative 4.9 t squared. And I'm going to get about 1.63 meters. I kept a few more decimal places here, so my answer might be slightly different. And therefore, and then you can use your grade 10 techniques if it happens to be a parabola. You can use them to make sure that that makes sense. So up here, like we know that the vertex should be halfway between 0.21 and 0.5, so that makes sense that it's at 0.36, and then subbing in the height. And here we've got the graph, so we can kind of just double check here. Does that make sense? 1.6, and yes, it does. All right, the last part of this question is, what is the instantaneous vertical velocity of the ball as it hits the ground? So if I'm looking for what is, so we want to know, what does this guy equal as the ball hits the ground? So if the ball is hitting the ground, then the height of the ball is got to be equal to 0, right? So h at t equals 0. So what we're going to do is take this information, we're going to find the t value that makes this true, and then we're going to plug it into the derivative. So I'm starting with h at t equals 0. I'm just writing it backwards here. Let's not do that. We'll say, I want to know, I've got my h at t, it's negative 4.9 t squared plus 3.5 t plus 1. I want to know, when does this thing equal 0? Now, this guy's got a bunch of decimals in it as coefficients, so I'm not going to be able to factor it. I'm going to use the quadratic formula. So the quadratic formula usually starts with x is equal to, but our variable is t, so t is equal to, and then it's negative b. So you might need to go look this one up. x is equal to negative b plus or minus. And I do expect that you know this for tests. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So just keeping that in the back of your mind, I'm filling that in here. This coefficient is my a, this coefficient is my b, and this coefficient is my c. All right, I'm gonna type this stuff under the square root into my calculator, and I get 31.58, or 85, sorry. And when I type these two into my calculator, so I'm going to type it in once with the plus and once with the minus, I get that t is either equal to about negative 0.219 or t is about 0.933. Now, a couple of ways that we can make sense of this. If I want to know when the ball hits the ground, I'm not going backwards into time. The other thing is in the equation, or in the question, it told me that t had to be greater than or equal to 0. So since I've got that restriction on my t variable, I know that this is the only answer. All right, so we've got this first part. We figured out when does the ball hit the ground. Now I actually want to find what's the speed of the ball as it hits the ground. Hopefully it makes sense that you should be finding a negative speed if it's hitting the ground. And so I'm going to just plug this this t value into my derivative because my derivative is what tells me the speed. Remembering the derivative is this equation. And then just typing that into my calculator, I get. And then you want to think about the units. So what are the units? It might make sense to you in this word problem. But if not, when I'm finding the units for a derivative, I'm always thinking about rise over run. Going back to grade 9, the rise unit over the run unit. Here the rise unit is the height, so the unit was meters, and the run unit was time, so the unit was seconds. And then we'll write a sentence here. They asked us about what happens when the ball hits the ground. And in my summary sentence, I'm always going to talk about direction. Whether it comes out as positive or negative, you need to tell me if that velocity is heading up or heading down, or if it's a sideways position function, you need to tell me is it heading to the right or the left. This one was negative, and so it's going to be downwards. All right, that's it for today's lesson. Have fun with the homework.